Okay, welcome everybody to today's webinar on Sirovision 6 and its new functionality. Just before we start, if anybody has any problems hearing me, just if you could type a message in the chat box, just let me know. But otherwise, I'll continue. And if you have any questions, you can either type them into the chat box and I will look at them and answer them after the webinar, or I'll display an email address and you can send me an email and I'll get back to you today about that. Okay. So it looks like we have quite a lot of people logged on, so hopefully everybody can hear me. The format of the webinar is that you can hear me, but I can't hear you, like I say, so any communications, do that through the chat box. The webinar should be around 40 minutes, 35 to 40 minutes. So we'll get started. To mention that Sirovision 6, I believe, is the 5th major release since 2012 from Datamine. So we are on target for 2 major releases of the software per year. And we have a fairly healthy roadmap and plans for Sirovision and its expansion. We've already begun work on version 6.1, and I will, if we have time, I'll just mention a few new features that we're going to add to 6.1, which we aim to release around August of this year. Okay, so hopefully you can see my screen. What's displayed is the webinar outline. So I'm going to go through all the major new features in Sirovision 6. The first of which is, this will be relevant to people who have used Sirovision before, obviously, but there's a new GUI design. We've reshuffled the windows and made everything a little bit easier in terms of workflow and simpler to use. So I'll cover that first. Then I'll go straight into the new slope stability analysis functionality, which is probably what most of you are here to have a look at. This is pretty much the direction that we are going with Sirovision in terms of expanding our analysis, our geotechnical analysis functionality. It's not so big a deal these days to be able to generate 3D models. There's a lot of software that does that. So Sirovision is really heading in a direction to add some valuable geotechnical analysis functionality. And this new functionality is the addition of block analysis to the existing functionality we had in previous versions. So I'll spend probably most of the time on that. Then after that, just show you the mineral classification tool. This is a basic tool to automatically map the occurrence of mineral colors in a 3D model and give you a surface measurement output on the occurrence of those minerals. And then after that, I'll briefly go through the performance improvements. We added this because there are a lot of new cameras out there with large megapixel sensors, getting up to 24 to 30, 32 megapixel cameras, which produce large images and thus slow down processing time. So we've added in some new functionality to give you options to reduce image and spatial resolution of images and to reduce file sizes. And lastly, we've added in some functionality to enable you to do analysis on larger areas of 3D images, which basically means merging 3D mosaics into single images and then doing your analysis work there. And I'll try and briefly talk about future developments in 6.1. So we'll just hop out of that. I'll open the software and start and show you the new changes to the GUI. So this is the new Sirovision 6 graphical user interface. It looks similar at this point to the last version. Close that down. So the biggest changes are in the old version of Sirovision 5.2, the last version. We had 3 tabs up here in the image view. We had a map image view, which is still here, and we had a mapping explorer tab and an analysis explorer tab. The problem was that when you were looking at analysis work or mapping work in these other tabs, you couldn't view the same objects in all your windows simultaneously, which sounds quite basic, but we should have done that in the last version. So in this version, we've just got rid of those two separate views, and we've just added a new window called Explorer. And basically here this Explorer window lists all the objects which you can map on a 3D surface. And there's some new objects here which I'll cover later in the webinar. But basically, if you click on something like discontinuities, it displays all the discontinuities, also in the stereo plot, and also in a new viewing window called Table View, which gives you a table view of the objects that you're looking at. So we got discontinuities, traverses, text annotation, survey points, survey lines, domains, imported structures, pore pressure grids, and mineral classification objects. So these new ones here, I'll talk about those shortly. So that's basically, so wherever you select on an object, it's highlighted in all the windows simultaneously, which obviously makes analysis a little bit easier. The old analysis view tab has been just added in here to the Explorer window also. So when you run an analysis set, then the analysis set is also displayed here with the same idea. If you click on something, it's displayed in all the views that you're looking at, rows plots or stereo plots, etc. Okay, so that's really the main reshuffle in the graphical user interface. The old Project Explorer is still here, and that lists, when you create 3D models, all the files for that are listed in here. So I'll just get rid of that because I won't use that in the rest of the webinar. So we've got the Explorer window here. Around the GUI, there's a few new icons, which I'll also explain what these are for with the new functionalities and mineral classification here, and show different types of blocks icon. And there's a little bit of a reorganization of tools in the stereo plot window which apply only to spherical projection analysis. One of the other new small features is a 3D dips facet view. So just gives you a quick indication of the dominant dip direction, and also one for dip direction here. So along with the wireframe, point cloud, and the 3D image functionality. So that's really the major changes in the GUI. The rest of it you could probably work out for yourself when you load the software. So I'll move on now to the new block analysis functionality. The image you see here is quite a nice image, demonstration image, which shows a nice natural wedge. Hopefully you can see that quite well. So basically, the new functionality in the slow stability tool is the addition of polyhedral block analysis. Now, before I talk about that, I'll just recap the functionality that was available in version 5.2, which was the wedge analysis, the tetrahedral wedge analysis. So this is what I'm showing here, which existed in version 5.2, which are automatically detected wedges on this rock surface. Now, the version 5.2 had a much more basic setup in order to detect wedges. In 5.2, we considered the whole 3D surface as a single domain. And for that domain, we would input geotechnical parameters over here in the property view. You probably find it quite difficult to read that, but we would input cohesion and rock density and a friction angle into that 3D image or 3D model, and it would apply those values to all the joint surfaces in the model. So it was really a single domain analysis. So when we would then map structure on that surface, like this, so these are the map discontinuities, we would then create an analysis set. So I'll just start a new one to show you how simple that was. Create an analysis set. And we create an analysis set we can filter out the data that we want to analyze, but in this case I'm just going to pull out everything which is in this particular image. I create a new analysis set. So this is my new analysis set of discontinuities, all listed here down here in the table view and up here on the stereo plot. To run the wedge analysis, what we would do then would be to create orientation sets, because the wedge analysis we're doing is it's just a simple analysis. We're comparing two orientation sets and detecting whether any of those two structures would intersect and daylight on the rock face. So that was also a very straightforward process. We just create two orientation sets. In this case, run that. It creates a red and green orientation set, dominant orientation sets. Then we simply click on kinematic sets, perform the stability analysis tool, open that, and we'd run this wedge analysis. So here below we have the new functionality, which I'll cover in a second, which is the polyhedral block analysis. But the wedge analysis, we'd run that, and this would open a screen where we would be able to input for both orientation sets. In this case we have a red and green orientation set. We would be able to input cohesion values and internal friction angle values for both sets. We would also importantly be able to use different persistence methods to analyze the structures. And this is very important, obviously, what persistence of the structures that you're looking at that you use in your analysis. So we had a maps option, which uses the physical persistence that we can see on the mapping itself in the 3D image. There was use a maximum for all of the structures. So the biggest structure there, we just use that largest persistence. And we also have a custom where we can input a custom persistence for that set. So the importance of persistence in doing wedge analysis is quite important, because it's the actual physical size of the structures, and what we're looking at is where exactly these structures might intersect to form a wedge. So the persistence is obviously important. The larger we make the persistence, then the more conservative the wedge analysis becomes. So just to show you quickly how easy that was in version 5.2, this is the wedge analysis. We'll just use the default values for cohesion and friction, and we'll use the mapped persistence. Actually, I'll make that custom, and we'll make it about 25 meters for each set. Custom persistence 25 meters. Okay, so we've got 25 meters persistence for both sets. I'll run that. And that is a very conservative method, but it detects a lot of wedges, which is displayed here. If I hit next and finish, you get this. You get a lot of wedges. That's a very conservative way to look at the wedges. But what we can do in version 6 now is, when we run that analysis, we have set a factor of safety cutoff. And the blocks, the wedges themselves are color-coded against that factor of safety. And each wedge is given a classification. Type 1 classification is unstable. Unstable wedges are tagged red. Type 2 are colored amber, and they're stable with friction. So any changes to the friction, cohesion, or pore pressure values, then that wedge could become unstable. And type 3 are stable without friction. They're marked green. So those are basically safe wedges. So if I just pick out one of these wedges, what we could do with the wedges is it will map the wedge with the this upper boundary is the persistence which I entered, which is 25 meters. So it's given each of these, this top release boundary 25 meter, based on two 25 meter planes intersecting, which are the two gold planes here. I can easily just click and drag that down to change the size of the wedge. And when I do that, it recalculates the size of the wedge and it recalculates the mass and the volume of that wedge. So I'll do that again with this one. Just drop it down to there. So it redraws and remaps that wedge. So that's basically the wedge detection functionality which is available in version 5.2. So with version 6, we have expanded that to add polyhedral block analysis. What that will do, that will look at the same structures, but it will calculate the existence of blocks. So not just looking at two orientation sets, it will compute all the interactions of all the structures that are mapped on the rock face to form blocks, and it will run the same process and map the blocks much along the same way as it matches wedges. But some changes that we've added to make that a little bit more sophisticated is in version 6 now we, instead of considering the whole 3D image as a single domain, we can now have two options to either map multiple domains in that 3D surface, or we can import a domain from another program as a DXF. So the idea here being, of course, that if you can map, most surfaces are made up of multiple domains with different geotechnical characteristics. So I'll just demonstrate how you can easily map a domain here, just a basic domain. If you click on the Add Geological Domain button, I'll just cut this image in half. So I'll just map two domains, and you just do that easily by left-clicking the boundary, the rectangular boundary, the regular shaped boundary. Right-click to close it. And what that does, it maps a domain. We've set it up this way so you can view the surface of the domain kind of from behind the 3D model, so it's a little bit easier to see what area you've set up in the domain, and you can do things like change the color just to make it a little bit more visible. Make that one yellow. And you can input the density for that domain and also the pore pressure coefficient for that domain. So I'll just go ahead and map another domain on the other side of the image. Oh, excuse me. That's not what I wanted. I'll do that again. Make sure I don't click on a structure when I do that. Left click and map another. So that's the second domain, and I'll color that one red. So now we can easily see, this is very basic, two domains, but like I say, we can import domain surfaces from other programs in DXF with their and add geotechnical characteristics to those domains. So this is very basic, but you can import irregular shaped domains and as many as you like, and easily just add some geotechnical characteristics to those domains. Okay, so we've got our domains. I'll just turn those off from the display, a little bit more sense. The second thing that we can import is pore pressure grids. At the moment, these are basic pore pressure grids as a text file. And I'll just open one up here. And these are very simple. It's just 4 columns of easting, northing, height, and the pore pressure in pascals. So this is just a grid, a sample grid of pore pressure measurements at this particular site. So we can import these, metric or imperial, so metric. And this is quite a basic one where we just had a sample pore pressure grid. Hopefully you can see the little colored dots, which are the sample sites for the pore pressure. So what this imports a pore pressure information which is used in the calculation of blocks and wedges, or the factor of safety, I should say, of the blocks and wedges. So we now have pore pressure information. Click on that. You can edit the pressures here as well if you need to, and in various places. So far we have our domains and we have pore pressure information input. We also have rock density values entered and internal friction angles measured, and cohesion values. So all of these measurements, all of these geotechnical values are used in the calculation of wedges and blocks. The last object or functionality we've added to the block analysis tool that we can import is the addition of complex structures or irregular surfaces. I don't actually have one for this particular example, so I'll just save that and load another image where we do. I have one for this. So this has some blocks already mapped. Again, we can map a irregular surface or a complex structure in other programs, and again import these into this Sirovision as a DXF file. So I'll bring that one in, and it's this interaction of the complex structure with the other structures that you've mapped manually. It takes this into account when it maps the occurrence of blocks and the factor of safety of those blocks. So we basically can import complex structures, we can import pore pressure grids, and we can import domains, each with their own geotechnical characteristics. So I'll just open up that last image again. So this one doesn't have a complex structure, but we do have our pore pressure grids and domains mapped. So basically we tried to make this tool a little bit more sophisticated and more realistic by having multiple domains, more detailed pore pressure information, and the inclusion of complex structures. So when we go to run the block analysis, again it's pretty simple. I'll just turn that off. Perform stability analysis. This time you select polyhedral analysis, block tool. And as I mentioned before, the block analysis does not require orientation sets, because it will analyze all existing objects and all existing structures on the 3D model. So if you have not already created orientation sets, it will just create one large set and it will analyze everything. In this case, I have a red and green orientation set up. So it allows me again to import cohesion values and internal friction angle values for these sets. And again, you can select different persistence methods to run the analysis. So there's different places where we can input a lot of geotechnical information to be calculated. Same for the green set. So I will just change the cohesion here to 550. That's in kPa. Friction angle 26.6. And I'll set up a custom persistence, again quite conservative, for these structures of 25 meters. Same for the green set. Custom. And that's it. Hit next. And hopefully it'll plot some blocks. Now this again that was using quite a large persistence. It's quite a conservative analysis, and it's found a lot of blocks in here. So again, the information that you get for each block is the classification, and this again is based against the factor of safety cutoff, which we've set, which is usually in a mine is about 1.1, 1.2, something like that. The blocks to which is mapped, we have classifications again. Stable, which is red, type 1. Stable with friction, which is type 2, and colored amber, and the third is stable without friction, which we mark them as green blocks. So we can very quickly see the dangerous blocks and the amber blocks and the safe blocks. You can order the output here factor of safety, so you can immediately see which are the most dangerous, go from top to the bottom. Some of them don't have a factor of safety. It's because they are stable without friction, so that means that they are not removable, they're not dangerous, they're not going to fall out of the wall, because they're no matter if pore pressure, friction or cohesion changes, it doesn't matter, they are safe blocks. So if I go ahead and plot that, I'll go back to this one. So in this case we have quite a few blocks because we ran quite a conservative analysis, and the amber blocks here are marked on the rock wall and also here on the stereo plot. This toggle up here, we can either show just the kinematically free, which means it's the amber or the red blocks, the unstable or stable with friction blocks. We toggle that, then we also show the green blocks, which you probably are not so worried about, so we can just toggle those back off again. So the idea, hopefully I'm demonstrating that it's very easy and quick to run wedge and block analysis against the structures that you've mapped. That now we can import complex structures, map multiple domains, and import pore pressure information, which produces a more accurate calculation of the factor of safety of the wedges and blocks which we're looking at. All of this information that you can easily put together, these objects can be exported from the software as DXF into other programs. So we're trying to make everything as compatible with other software as we can, but it's increasingly looking like people are using Sirovision and importing data into Sirovision to do this analysis rather than what used to happen in the old days where we just export data out of Sirovision. So I guess it's good for us that people seem to want to import other people's data into Sirovision these days. So this is a very brief overview of the block analysis. We have some more technical documentation on this, which I'm happy to send to anyone who wants to have a look at it. And we're also putting together some more detailed training videos. So just to stay on time, I'll move on to the rest of the other new features in Sirovision. The next thing I wanted to show you that was new and was added in request from some of our users was the mineral classification tool. Now what this does, I'll just run it on, excuse me, I'll just open a different image. So the idea behind this request was that users wanted to be able to quickly and easily map ore bodies and calculate ore body volume. So the beauty of photography and the richness of the colors that we can obtain with photography, we're able to, with this tool, automatically map the occurrence of the colors of anything on a rock surface. In this case, what we're looking at is an open pit coal seam. The way this works is very easy. You just select a typical sample area of the ore that you want to map. So I'll just click a little rectangular area. And so everything in this, all the various colors in this rectangular area will be scanned through the image and will be automatically mapped. So see how quickly it mapped that almost instantaneously. So it's quick and easy way just to have a surface area calculation of a particular ore body or anything with a certain color. This little graph down here with colors and photographs, that they're a single color with many intensities. So what this graph allows you to do is just to tweak the minimum and maximum intensity range of the colors that you selected, which will change the output, which is mapped. So if you run the analysis and you get a little bit too much, or it's picking up a too wide a range of intensities of that particular color, then you can narrow that range down to make it a little bit more definitive. So that's the general idea behind it. It was requested by people who just wanted a quick and easy way to calculate surface area of mineral bodies and ore bodies. So if I extract those features, the software will plot that as an object and list it under the Explorer tab here and call it a mineral classification. We've called it a mineral classification at the moment, but we will probably expand this tool to automatically map different types of features. We'll probably expand that in 6.1 and further versions. So the software is just plotting that object, and when that object is output, it will give me a surface area in square meters of the occurrence of that mineral or that ore body. And that object, those objects are then exportable via the export wizard. So what I got here is just mapped the range of colors for that ore body that I selected. So that's really it very basically. I can run this multiple times, so I've got, if I want to run it for different types of ore, different types of colors, I can run this and save all the object results here under the Explorer. Like I say, I can go into the export wizard and export that as a mapped object. And here we have mineral classification. We can export the DXF and a text file, which is the surface square meterage of all of the map features. So very basic, that's a mineral classification tool. Obviously, you can run that on much larger objects, on much larger mosaics. Okay, so that's the mineral classification tool. The last thing I want to show you is the performance improvements in Sirovision. We've had a lot of demand for this. Some other software has been doing demonstrations, creating 3D images very quickly. But as it turns out, they're running those demonstrations against very low resolution images, which obviously low resolution images produce a low resolution point cloud. If you're going to do geotechnical mapping on that, it's quite dangerous. So we have added in the ability to reduce resolution, but it's quite important that people understand the difference, the trade-off between resolution and structural mapping accuracy. So I'll just show you the new image and spatial resolution reduction functionality. If we start a new project, camera, 3. Just quickly import 2 images. So we'll just process 1 image just to show the functionality. This is a file naming schema, so you can automatically rename all your files. So the software works at this stage the same as version 2, where it will import your left and right photographs from your camera or your stereo camera, underground stereo camera, whatever source you have, and will convert them into either 8-bit or 16-bit TIFF files. It will also apply the calibration information at this stage. So if you've captured the image as 16-bit, it will use 16-bit at this stage, or if you've captured them as 8-bit. I think when you actually take photographs with a digital Nikon camera, it captures them as 12-bit actually. So it will keep the bit intact at this stage. But this is a new screen. What this is, it gives you three options to reduce the image resolution of your photographs. This is because I mentioned at the start that new cameras have very large megapixel sensors, 24, 32 megapixels, and they produce photographs which can be 110, 140 megabytes each. So as you try and process images that size through software, it takes longer to process. It slows everything down. So we needed to add in a method to reduce the image size without compromising the quality of the point cloud or of the wireframe, therefore, so you don't compromise the quality of your structural mapping. So we have three options which we've added. We've added in an option to reduce the image size by 75%. Now, the image size refers to the surface image photograph, and this is what takes up the bulk of the file size. So what we've done here, we have a graph which reflects the pixel size on the face in millimeters to give you some indication of the lens which you've used, and the camera and the lens which you've used, the distance to the face, and the kind of linear 3D image extent and pixel size that you will get with that. Now, as I make changes to the image resolution, this will change, but also down on this side of the screen, there's the estimated size of the resultant image after you've reduced the resolution. So here, you probably can't see this, but this image is 96 megabytes because it was a 24 megapixel camera. So if I click to reduce the image size by 75%, that will reduce that image down to 24 megabytes at this stage. So by reducing the image size or the photograph textural image, it reduces the image down by considerable amount, 75%. But the point cloud data behind it, what you map structure on, is intact. So you can reduce the surface image resolution right down to reduce your file size and your processing speeds, but you'll keep the wireframe, the point cloud intact. So the second option we have here is to reduce the image to 8-bit. Now, our stereo camera records data in 16-bit. So if you have shot it in 16-bit, 16-bit is the color depth. And if you're doing geological mapping, for example, you may not need so many colors in your photograph. Most of the time it's overkill, you don't need that much. So we're going to reduce that down to 8-bit, and that actually halves the size of the image again. So now we're down from 96 megabytes to 12 megabytes. But still we have the point cloud and wireframe are still the same resolution for structural mapping. This last option here is a special point density of the point cloud. So Sirovision defaults to 3 pixels per special data point. This is basically your point cloud density. So we've added in some options here to reduce the point cloud also. If you don't need the amount of accuracy that you're getting, if you're just doing a quick geological analysis, for example, you can put this right down to 9 pixels per special data point, which makes the point cloud less dense and therefore much quicker to process in the software. You can also increase this value to 1 to make it more dense. So if you're doing geotechnical mapping, then you probably want to do that. You want to get the highest accuracy possible on your point cloud for structural mapping accuracy. And this is where Sirovision might be a little different from some other 3D image acquisition programs. Our capabilities of point cloud density and accuracy are very high. So if you're doing geotechnical mapping, you obviously want to map on the most accurate data you can get. So this option here, I've reduced the image quality down by 75%. I've reduced it down to 8-bit, but I've actually increased the point cloud density to 1 pixel per special data point. So I've reduced my file size, but I can still map my structure accurately. This is basically set up so you can look at your own requirements. If you're just doing geological mapping, then you can definitely get away with reducing the resolution right down, and it's still good enough for you to be able to map geological boundaries. Maybe with geotechnical analysis, you want to keep everything as accurate as possible, but you can still reduce the image resolution. So I'll go ahead and do that with this image. And when you do this, because of the much smaller file size, you'll find that the 3D image processing is sped up exponentially. I've been creating 3D images in 40 seconds or less than a minute. So in the past, it might have taken 5 minutes to create a 3D image. Now, if your requirements suit lower resolution, then you can create these in 40 seconds. So look, I'll go ahead and build a 3D image, hopefully to show you how quick it is. Hopefully it does what I hope it will do. We probably have about 5 minutes left to run. So we'll just finish up with this, and then I'll put up an email address. If you have any questions about what I've shown here, then send me an email and I'll get back to you today about that. So right now it's done the task setup. It's just running the matching between the left and right photographs. And in the past, this is what has taken as long as 3 minutes to 5 minutes to complete. So it's just done that. And now it's creating the 3D image. Haha, that's a known bug. Excuse me a second. Let's get out of that. That's what happens when you use a beta for a demonstration. Let's start the program again. Okay, load the project. Let's run that again. So it's just creating a 3D image. So I just want to show you the having reduced the resolution right down, what kind of picture quality you actually get here. So this is a reduced resolution image, which processed in probably 40 seconds, 30 seconds. And you can see that it's still, in terms of textural surface, it's still definitely accurate enough for geological mapping, at least. So hopefully that will speed things up for our current users in terms of processing data. The last thing I just want to show you that is quite important, I'll close that image down, is now that we're able to create lower resolution images and work with larger data sets as a consequence, because each file is much smaller, it doesn't choke up the memory of the program. We've added a function now where we can merge multiple 3D mosaic files into a single file and then do our analysis on large scale images. So this is the new merge image files functionality. Basically, you can pull out a mosaic, a 3D image or a 3D mosaic from anywhere. If it's georeferenced and they're obviously all in the same georeferencing grid, then you can merge them together into a single image. So I'll just bring in two mosaics of a open pit. So I've got 1 and 2. So these are this first one is 420 megabytes. The second one is 230 megabytes. So reasonable size. Bring those into the wizard. Let's minimize it again so people can see it better. So I've got my two mosaics. I've got the original file size. And what we've got here is we have another chance to reduce the image resolution down between a factor of 1 to 10. So we can really dramatically reduce the size of these files. So if I put it in a factor of 8, say, this will reduce the image and the spatial resolution of the images by a factor of 8. So the recommended workflow is that you do your structural mapping on these mosaics first, and then you merge them and reduce the resolution and build a single image. And this will keep your structural mapping intact with the same accuracy as when you mapped it on the full resolution image. So I'll go ahead and merge that. So what it's doing here, when I put in the image reduction factor, it gives me an indication of the resultant size. So I've reduced this whole mosaic down from 700 megabytes down to 10 megabytes. So now it just says, what do you want to call the new mosaic? And that saves the new mosaic. So I'll just load that in. New mosaic. And as I said, when you do this, you do not lose your structural data. So these are the two mosaics was a half of this open pit, 2 halves. I've just merged them into one single large model. But the structural data that I'd already mapped on the full resolution mosaics is still intact here. So hopefully this shows you that you can now merge a lot of data together into one big 3D image and do your structural analysis and wedge detection, block analysis on that image. So that's the merge mosaic option. So we've really tried to set up Sirovision to better cope with larger megapixel cameras and larger image sizes to allow you to better manage your file sizes and your ability to work with larger areas. So that's a bit of a quick run through. We've been running for 50 minutes, so I've ran over time. I'll just put up this. I haven't done that very sophisticated. I'll put up my email address here. Hopefully you can see. So if you have any questions about this webinar, we've recorded it also, so we'll put it up on the DataMine website. If you have any questions, please email me, and I will get back to you on this and send you some more documentation if you require it. Okay, thank you.